Okay, welcome back to the second part. So I left you with the exercise to calculate the effective temperature of the sun, given the luminosity and the radius of the sun. So obviously we're going to apply this formula that derives from the black body radiation concept, introducing the idea of effective temperature here. So we need to rearrange the equation to make what we want, the temperature, the subject. So that leaves us with this term on the right, and then we just need to put the numbers in. So we can put in the luminosity of the sun, we can put in the radius of the sun here, and this is the Stefan-Boltzmann constant, 5.7 times 10 to the minus 8. And if you calculate all those numbers and take the fourth root, then you end up with back at 5,800 Kelvin again. So showing you that this is how these three variables for stars, so key variables really, luminosity and temperature, we will be referring to throughout the entire time, and the radius, the size of the star, so linked through this equation. Okay. So now I want to introduce another key variable here, which is flux, and to show you its relationship to luminosity. So normally we wouldn't be determining the luminosity of a star by using its radius and temperature, because often, as you will see, in workshop 1, you'll see that we can't usually measure the radius of another star very easily. So this is where the concept of flux and measurements with telescopes come in. So we can determine the luminosity of the sun or any star by finding the total flux of radiation reaching the Earth. But of course, we're going to need to know the distance as well. Okay, and this will all become clear in the next few slides. So a little bit more about flux. We're going to formally define it in a moment. But basically, when we look at the spectrum, as I mentioned earlier, taking the broadband distribution of intensity as a function of radiation, as a function of wavelength, then it's the flux is the thing that we're actually measuring there, okay, as a function of wavelength. So that brings us to this formal definition. So we haven't got too many of them in this module, but here's one that we definitely need. So I'm going to define something called monochromatic flux, okay? So the name derives from mono, meaning a single, and chromo, meaning a color. So this is like the flux at a single wavelength, basically, a single color. So the monochromatic flux of radiation, I'm going to give the symbol F sub lambda here. So the F for flux and the subscript lambda, indicating that it's a function of wavelength. So F lambda is defined as the amount of energy crossing a unit area per unit time and per wavelength interval. Okay. So it's a little bit of a mouthful. Okay, so let me go through that again. So the monochromatic flux, F lambda, is the amount of energy crossing a unit area per unit time per unit wavelength interval. So sometimes seeing the units helps get a feel for what we're talking about here. So it's the number of joules per second per meter squared, representing a unit area. And officially, of course, in SI units, the unit of wavelength would be a meter. So that's per meter representing per unit wavelength interval. Now, in reality, of course, we would hardly ever use per meter as a unit of sort of wavelength interval and wavelength. In the optical, we're often talking about wavelengths in nanometers, as we shall see. And so you might often see flux written differently. Of course, joules per second, so energy per unit time, is also a unit of power. And so often you will see it written as watts per meter squared and then per some wavelength interval unit. So here I'm just illustrating this with per nanometer. Okay. So obviously that isn't an SI unit because it's per nanometer. So if you're doing calculations, you need to put it in SI units. Okay. So that's the formal definition. Now, to sort of show you graphically what we mean, so let me take you back to a diagram similar to what we had in the first part. So you've got a spectrum of the sun here now in a bit more detail. And again, you've got black body curve superimposed on the top here, but that's not particularly relevant here. What is relevant is what I've drawn here. So this is the idea that the monochromatic flux effectively is a particular data point on this spectrum somewhere. Okay, so it's the flux at a particular wavelength. Okay. And you can see the units here. They are indeed, this is a unit of flux, watts per meter squared per nanometer. Okay. And here's the wavelength in nanometers going up here. Of course, in practice, you can't measure the flux in an infinitesimally small wavelength interval. You have to let some energy in, and so that will normally be over some small range of wavelengths, which I've indicated with delta lambda here to represent a small range of wavelengths over which this data point has been measured. And so that will always be true. And then the units are taken care of when this, you divide out this to get a per unit wavelength interval. Okay, so that's graphically what monochromatic flux would look like. And if you're basically trying to build up the spectrum of an object, you need these data points at all, a series of data points across this curve in order to define the shape. So at several different wavelengths. Okay, so here I want to illustrate that flux is the fundamental thing that a telescope actually measures. Okay, so here's a schematic diagram of a telescope. Okay, so we've got it's a reflecting telescope. We've got a primary mirror here. So the light rays are coming in from the sky from the left-hand side. You see these light rays coming in here and here. So these light rays are parallel, obviously, because stars are basically at infinite distance. So the light rays are coming in parallel. The light gets collected by the primary mirror, usually bounced off a secondary mirror here and down to some detector at this end of the telescope. Okay. So often you will want to define the wavelength range of the light falling on your detector. And so to do that, you would normally put some kind of color filter in the path here that will only let through a certain range of wavelengths, which I've again illustrated by delta lambda here. It could be a broad filter that lets through all the red light, or all the blue light, or even all the visible light. Right? But there will always be some range of wavelengths over which your detector is detecting. Okay. Now, when you expose with a telescope, you will expose for a certain amount of time. Okay? That would be your exposure time, just like taking a photograph, for instance. You expose for a certain amount of time. With modern detectors, you're integrating on your detector for a certain amount of time. And your detector, fundamentally, is detecting the amount of energy that is falling due to the light, due to the photons falling on it. And your primary mirror here will have some kind of geometric collecting area, okay? So if it's a circle, how big is the area of that circle of that mirror? So what does a telescope do? Okay, it measures a certain amount of energy that is falling on this cross-sectional area here, passing through a certain wavelength interval over a certain amount of time. Okay, so that's flux, right? So it's the amount of energy per unit area, per unit time, per unit wavelength interval. Okay. So this is exactly what a telescope measures. Okay. So that's why flux is so fundamental, because basically it's the starting point for everything we do with it when you're observing radiation with a telescope. Okay. So to make the relationship back to luminosity, we need to next introduce another quantity, which I'm calling the total flux. Okay. So now, rather than worrying about per wavelength interval, we're trying to add up all the flux over all the wavelengths. Okay. So total flux, which I give the symbol F without the subscript lambda here, the total flux of radiation F is defined as the amount of energy crossing a unit area per unit time. Okay. So that's basically exactly the same definition as before for monochromatic flux, but this time there's no mention of per unit wavelength interval. It's over all wavelengths. Okay. And obviously, all the type of energy we're talking about here is always the energy in the radiation itself. So this has simpler units. It's the amount of energy per unit time per unit area. So that's joules per second per square meter. Or again, if you want to put watts in here, it's just watts per square meter. So that would be the units of flux, total flux. Okay. So as I mentioned, this is really the sum of monochromatic fluxes over all wavelengths. And if you want to write that mathematically, then you could just write it like that if you want to. But you can think of it as summing up all of those delta lambdas to give you the total area under the spectrum. So graphically, you can look at it like this. So this is that same spectrum again. So here I've now hashed in the area under the curve, if you like. And so that area would be your total flux. That's exactly what we're talking about. The integral under that curve, if you like, is the area, of course, as you know from calculus. Okay. And a point I should have made earlier, really, that formula for luminosity, the sigma t to the fourth formula, also comes straight out of the mathematics of the Planck function. Okay, so again, this would be more of a challenge for the mathematically interested amongst you. If you take the Planck function and integrate it over all wavelengths, you come to that sigma t to the fourth part of the formula, the amount of energy per unit area radiated by a black body. Okay. Now, that's a bit more tricky of an integral to do. I don't think you'd know how to do it until those of you on the physics course have done a bit more mathematics. But it's doable. And you can see that because the Planck function is a function of wavelength and temperature, if you integrate over all wavelengths, the only variable left is t. Okay, and that's why you get the sigma t to the fourth dependence. Okay, but again, that's optional. You don't need to worry about that. You just need to be familiar with the sigma t to the fourth formula. Okay, so this is the idea of total flux. Okay, so you know, in practical terms, you could measure lots of monochromatic fluxes at different wavelengths using different color filters, and then you could either put a curve through here and get the area, or you could just interpolate and add up all the area that way. That would give you the total flux. So how do we relate luminosity and flux? Okay. Well, again, let's just take the example of the sun, but again, it's true for any star. So remember, luminosity is the total amount of energy per unit time that a star is emitting in all directions. And then flux is the amount of energy unit time per unit area falling at some particular location, some distance away from the source of the luminosity. So d here is the distance away from the sun or the star. And this is easier to explain geometrically in a moment with a diagram, but let me make a couple more points first. So a key thing here is that, for a given object, let's say the sun, with a given luminosity, the further you are away from the object, the further you are away from a star, the flux drops, okay? And it drops with the inverse square of the distance. Okay? So this is a classic inverse square law, okay? So it's an inverse square law for the flux of radiation. And we can turn that equation around to make L the subject. And this is probably the formula I'd like you to remember and to use. Okay, so in more practical terms, if we want to determine the luminosity of a star, we can measure first of all, its total flux by adding up lots of monochromatic fluxes. And then if we know the distance, d, then we can multiply by 4 by d squared to give us the total luminosity. And so this is how you would measure traditionally the luminosity of a star from its total flux and distance. Okay, so let's go back to this formula here and illustrate where that formula comes from. Okay, so there's a little diagram here. Okay, so imagine you've got your star at the center here, which you can effectively think of as a point of light. Okay, and a key thing to remember here, of course, is that radiation, light, travels in straight lines. Okay, so you've got these dashed lines are representing light rays coming out from a point source of light here. Okay. So that object in the middle there has a luminosity L, so it's pumping out radiation with so many joules per second there. But at some distance away here, so it's switched to R just because we've got a sphere here, but it's the same as the D on the previous slide. Okay. It's the distance away that we're measuring the flux. So the flux here is how much energy per unit time is passing through this unit area here. So how would we determine that mathematically? Well, we've got a sphere here. Okay, so this circle represents a sphere all the way around. That's with a radius r. So if we want to know, and obviously it's going to be uniform. The star is emitting isotropically, as you would say, the same in all directions. Okay. Surface area of a sphere, again, is 4 pi r squared. Okay. So if we want to know the amount of energy per unit time per unit area here, we just need to divide by the total area of that sphere, which is the 4 pi r squared. So you can see, again, so if this was a distance d, then this is L over 4 pi d squared. So that's where that formula came from. And this next diagram, again, comes from the universe textbook. It's just illustrating this idea of the inverse square law. Okay, so imagine you've got a star in the center here. And again, you can put these sort of imaginary spheres around it at ever increasing distances. And think about a sort of cone of light coming out here, which is represented by these squares that are getting bigger in the area. Okay. So, but because light travels in straight lines, the total amount of energy going into this cone per unit time is going to be constant. Okay, so you've just got a segment here, if you like. But at this closer distance, illustrated by d equals 1 here, then all of that energy is going through that square. But by the time you've doubled the distance, that same amount of energy is now spread over 4 squares. Okay, so you've gone twice as far, but now the flux in any of these squares is 4 times lower than it was here. Okay, so that is your classic inverse square law. The flux here is now a quarter of what it was there because we've doubled the distance. And the same thing here, if you go up to 3 times the distance, that same amount of energy is now spread over 9 squares, and therefore 9 times the area, so therefore the flux is now 1/9 of what it was at d equals 1. Okay. So this is classic, what I would also refer to as geometric dilution. So as you go further and further away, if you've got something that travels in straight lines like radiation, then you always get this inverse square law type dependence. You'll see the same thing in other areas of physics. If you look at the electric field from a point charge, it does exactly the same thing. You've got an inverse square law there, Coulomb's law. If you've got the gravitational field from a mass that acts through a center of mass here, same thing. The gravitational field drops as 1 over the distance squared as well. So anything that acts through a point, if you like, will have this inverse square law. Okay. So let's summarize this lecture. So the sun and every other star pretty much radiates from their surfaces very much like a black body. So we've introduced this idea of black body radiation as a very useful concept for starlight. We've seen 2 concepts that flow from basically black body concepts and the Planck function. The first is where the peak of the Planck function lies is determined solely by the temperature of the star. So that's Wien's displacement law. And of course, we're already on the game here of how are we going to determine properties of stars by just looking at their radiation. So one key property of a star is its surface temperature, effective temperature. So we've already seen one method that we could measure the temperature of a star. We could plot out its continuum spectrum, find the peak, and just use Venus displacement law to estimate the temperature without ever visiting the star and sticking a thermometer in it. And similarly, we've now seen a way in which we could determine the luminosity of a star, how powerful a star really is. Okay, we could find that by, first of all, measuring its total flux, by measuring lots of individual monochromatic fluxes and adding them all up, and then to give the total flux, and then use the inverse square law. As long as we know how far away the star is, we can then scale that back to work out the total luminosity that it is emitting. Okay, so two fundamental things that we're going to come back to time and time again. Okay, so as always, a little exercise to leave you with for this week. So I'll leave you the exercise of evaluating the total flux of radiation from the sun that's reaching the Earth. Okay, so you can go back and look at the list of properties that I introduced you to for the sun in the first lecture proper, and use the formula we've just discussed to compare, to evaluate the total flux of radiation from the sun reaching the Earth. So that would be over all wavelengths. Okay, and just for a bit of fun, really, and you know, to get you thinking, why don't you just go and look up the typical power output of a typical solar panel? So just go and look, Google one up and have a look, and see how those two numbers compare. Okay. Give you a little insight. See if you're on the right track. Okay, so that's it for this week. Next week we'll go on to look at the more properties to do with flux and measuring the brightnesses of stars, and also their colors and the other ways in which we can determine the temperature of stars more accurately.